Okay. Yes. Do you want to show me at the end of this class, or do you want to see me later today? Because I'm free after lunch. Yeah.
We had 3 periods of chemistry after lunch.
Yeah.
At what time? 2?
2 to 5.
So, maths at 1, chemistry at 2, 3 and 4. Oh, I feel so sorry for you.
Thank you.
Why do you have 3 hours today?
From, I think last week, every Thursday can be 3 hours of chemistry. Why couldn't have been 3 hours of physics?
Inhumane. Huh?
You can go fight with Laureate, make it like 2 hours chemistry, 1 hour physics.
Put a physics in the middle, just to break it up. A chemistry physics sandwich, yeah? We'll think about it. Okay. Alright, this is what we'll have a look at. Is that okay? Yeah. Okay. So last time we talked about decay. Do you remember the 3 types? What are the 3 types? No. Don't look. What are the 3 types of decay?
Radioactive decay.
No.
Alpha decay.
Alpha, beta, gamma. Alpha decay, beta decay, gamma decay. Okay, good. Now, so this is what uranium looks like, and uranium is something which is radioactive, so that means there's alpha and there's beta that comes from it. And we learned that an isotope like uranium-239 will decay. The energy is released from uranium via alpha, beta and gamma radiation. But how can we detect this radiation? So how can we know there's radiation coming from it? In fact, all these forms of radiation are colorless. There's no color. You can't see alpha, beta, gamma. So you can't see it. Odorless, what does that mean? You can't smell it. Tasteless, can't taste it. Don't even think about doing this, it's very bad for you. It will kill you. And it's chemically inert. What does that mean?
It won't react.
It won't react, yeah. So it's neutral, it won't react. So it won't cause a chemical reaction. So it's very important we know how to detect radiation because it's bad for our health, since it's so dangerous. Okay. So what I'd like you to write down is the fact that radiation is colorless, odorless, tasteless, and chemically inert. Okay, you got that? Yeah? Does anybody actually know how to detect radiation?
The radiometer.
Yeah. Yeah. Makes sense, doesn't it? radiometer, yeah, for measuring radiation. Yeah, okay. So before we get to how to measure it, some more words. I do like radiometer. Okay, so activity. So it's the rate at which the unstable nuclei decays. So, for example, if the activity is high, it means, oh, there's lots of alpha and beta coming off from it, and very quickly is decaying. And if the activity is low, it means a little alpha and beta is coming off. Why today what?
Why did there so many people?
So many people?
Yeah.
You mean the children?
Not the children. In canteen?
Yeah, the students, yeah. They're summer students from, I think, Italy or Spain?
For traveling?
For summer English.
Living here?
Yeah, they live in the campus and they take English classes.
Because of them, we had to move rooms
When?
last week.
Really? They took your room?
Yeah, because they wanted to place all the students in the A block, and we were in the A block, and at the bottom floor, so we had to move upstairs.
But we're in the A block now.
Yeah, we have to move upstairs, and they live downstairs, and my previous...
Oh, the room you're living in?
Yeah.
I see, they wanted all the students on the same floor or something.
Yeah, like the same part, and Lisa's room was on the floor, so then they had to move to the B block. So, our Sunday was spent moving.
Exciting.
Sunday morning.
Exciting. Because of those students. Did they give you anything nice to make you move? Like, did they give you like an extra week for free, or?
No.
That's terrible. They should have said, oh, sorry for the inconvenience, please have one extra week or something.
I hope.
Disgraceful. Alright, so we have our unit for activity called the bequal. I am probably saying it wrong because it's a French name, so I just call it the BQ. Now what is the bequal? It's the SI unit for radioactivity, and 1 BQ is 1 destruction per second. So if 1 atom is destroyed in 1 second, we call that 1 BQ, a disintegration per second. Yep. Continue? Okay. So, in other words, when 1 nucleus is destroyed due to radiation per second, we say that activity is 1 BQ. BQ? The number's usually very big, so like, it's usually like 1 million BQ, 1 million atoms per second.
It destroys 1 whole nucleus in a second.
Now, you have your uranium, and let's say 1 million atoms decay into alpha and beta, then we say the activity is 1 million BQ. If 1 million atoms destroyed per second. No? Or yes?
How
to measure that? I'll show you shortly. use something called a radiometer. No. Use something, well, I'll show you in a moment how to measure it. So just before we do that, just some letters. A is for activity, and the units are BQ. For example, 5 kilo equals. N is for number of atoms. For example, 10 to the 6 atoms. Please note, sometimes I'm careless with the A. What I mean by that is, the A really should be a minus number. Why do you think it should be a minus number?
What?
The A. Really, maybe it should be minus because you're losing the atoms. They're being destroyed. For example, here. Sorry. So for example, come on. Here's uranium. And off comes alpha, beta, gamma. So really, maybe I should say the activity is minus 3 equals, because you're losing maybe 3 atoms per second, you know. But we don't really care so much about the sign. The sign is not important because you understand what it means to say 3 equals 3 destructions per second. Some people put in minus, some people don't. Can it get bigger? Yeah. Is it possible?
Dear teacher.
Possibly, but I have never seen it. But just like with acceleration, we can drop the minus if we use the right words. So for example, if I say deceleration, what does that mean? Deceleration. Not acceleration. Yeah, slowing down. So then I don't need to write the minus. Yeah. So you could say the activity rate for destruction is 5. So because I said for destruction, you understand that it means the atoms are being destroyed. Calculating N is not too difficult. You learned how to do this in materials. You remember, like for example, you can use Avogadro's number. Remember Avogadro in chemistry as well? So calculating the N is not so difficult. And you learned how to do this in chemistry too. So you definitely know how to do this. For example, 12 grams of carbon will have... Oh, I should have said 12 times this, shouldn't I? No, it's okay.
No, it's correct because it's 1 mole of carbon.
Oh yeah, sorry, 12 grams is 1 mole of carbon, so that's 1 Avogadro number of carbon. Yeah. No, the only thing I really care about is knowing what the A and the N stands for. Yeah. Do you understand the A and the N? Okay. This is how you measure radiation. Maybe you want to write its name down. Call it Geiger Mueller counter. Huh? Yes. Or yes. I don't know, I like red. I like it. This is the name of it, Geiger Mueller counter. Geiger Muller. Named after Mr. Geiger and Mr. Mueller. Not this picture, another picture. Ah, good coffee. I need it. Okay, let me play something for you. Now the speakers don't really work, but I'll try it. We'll see what happens. Come on. Let me close this. Right, where's the volume? Playback. Maximum volume. There we go. Now the sound's not great. My speakers are broken, but it should give you the idea of what this machine sounds like. I think maybe you've heard it before on TV or in a movie, maybe. Ghostbusters? No. Can I make it louder? Try again.
Yeah, the one in Insidious and in The Conjuring.
Yeah. No? Yes, maybe? Yes, it does sound like a radio broken. It has the same sound. Yeah? So what happens is, yeah, it does. No, it's a very old machine too. I guess I can close this. So what happens is every time the alpha or beta radiation hits the detector, it makes a click sound. So when many of them hit the detector, it makes many clicking sounds. So it sounds like a broken radio. The click sounds. It sounds like a broken radio. Yeah? So if it's noisy, it means there's lots of radiation, and if it's quiet, it means there's no radiation. That's how it works. So this is the Geiger Mueller counter. So let's see exactly how it works. I'll explain here. Okay. So how does it work? Right, so don't draw this yet until I explain how it works. So you have this special glass here, mica window. This glass is very fragile. It easily breaks. So if you drop this, it probably is broken. The glass here is very thin glass. So the glass is so thin, it can let the alpha and the beta radiation in the machine. Okay, so it's very thin, very delicate. So what you have here, this one, let me see. This one is negative, and this one here is positive. So you have an electric field here. And do you remember the formula for electric field strength? It's voltage divided by distance. Now, alpha, what's the charge on alpha particle? Do you remember? +2, I think. Yeah, and what about beta? -1, yeah. So if you have an alpha particle that comes in here, and if this is negative and this is positive, where will the alpha particle go? It'll go up, won't it? Yeah. And if it was a beta particle, it'll go down. Okay. So when the alpha and the beta hit this, the charge then travels along here. You have a circuit at 500 volts. So what happens here is this is actually just like a voltmeter. So it should be 500 volts, yes? But when the alpha and the beta hit this, it changes this voltage. So for example, if an alpha hits here, I think it will increase the voltage. It won't say 500 volts, it will say something bigger, because you have more charge then, you know. And likewise, if the negative, the electron hits the negative, the anode, also you'll get a different voltage. So this counter, all it's doing is it makes a sound if the voltage is not what it should be, if it's not balanced. So if you don't have the right voltage, then it starts to make a noise. So really, it's a very simple machine. It has 3 parts. Battery. Oh yeah, now the reason the resistor is here is because this voltage is so big, it's just to protect the machine. So you have cell, and resistor, you have something which is like a voltmeter, and this here is a vacuum. Okay, there's no air inside here. Now, what happens if you break this and the air comes in? Then it won't work, because remember, the alpha particle is really easy to stop, isn't it? Remember, the alpha particle is easy to stop. You can stop it with your hand. So if the air fills up in here, some of the alpha particles can't make it inside. It's too difficult. The alpha particle is so easy to stop, you can stop it with even just some air. Okay? So this is why it must be a vacuum for the alpha particle. Now the beta particle, it might still work with the beta particle if it's broken, because the beta particle can go through your hand, so it's not so easy to stop. But I don't think it'll work so well, because the electric field here, it doesn't really work so well if it's not a vacuum. The field here is not as strong. Anyway, this is how it works. I think also there is some gas put inside as well at low pressure, like a neon gas, and it's just to help. It's just to help detect the alpha and beta. So, for example, here, if an alpha particle comes in, but maybe the alpha particle doesn't hit the anode, the alpha particle would maybe separate an electron from neon. Because you know, if the alpha is positive, it should try and pull an electron off. Anyway, this is not really on the exam. I don't think they ask you to explain how it works, but they might ask you to say what you can use to measure the radiation. Okay, I would like you to draw it though. I don't think they'll ask you this in the exam, but I can double check. Let me double check for you actually before you write it down. Have you seen these in TV shows? No? So they go around and they...
With the antenna.
Catch
Yeah.
the boat.
Yeah, you see, this
So
is...
they check if like the ghost is in the room.
You see, this is because Ghostbusters is out. It's nothing to do with Ghostbusters. Before Ghostbusters... Really? This machine, not a ghost machine.
I mean, it makes the same sound, so I'm assuming it's the same machine.
I don't know about this. Right, let's just have a check here.
No.
You can't read as quick as that, can you? Yeah, don't worry about it. So they're not going to ask you to explain how this works, but I still would like you to draw it anyways. And it's not on the picture, but the gas in here is a low pressure neon. It's nearly a vacuum. Drew it already?
No.
You know the word ionize, don't you? In chemistry, how do you ionize? What do you do?
Use the electrolyzer.
Yeah, but what's the process for ionizing the gas?
You bombard the atom with electrons.
Yeah, so here what happens is you bombard the neon with alpha particles. And if the alpha hits the neon, it will pull an electron off, ionizing it, so the electron can hit it then. Yeah. But I'm pretty sure that the alpha can also just hit the anode as well. These are easy to make. In fact, you can make them at home.
The alpha or is the cathode of the anode ray?
I actually, now that I think about it, Hareen, I think in reality it's too difficult for the alpha to actually hit the cathode. I think what will happen is it's more likely it will hit a neon atom before it reaches the cathode and ionize the neon atom. But it should hit the cathode, yeah, because cathode is negative. Okay, continue. No.
The pink.
Pink. Oh, here, the purple. This is an electron and an ion. So what happens? So he is. You know the word ionized, don't you? The alpha particle can hit a neon atom, and the neon atom is ionized. The ion moves away to the bottom, and the electron that's freed moves up to the anode, which is a positive charge here. Is that okay? Yeah. So, Hareen, John told me you were trying to eat Rice Krispies in class yesterday.
No.
What?
You had a big box of them or something.
Andy gave me Rice Krispies.
Oh, it's Andy's fault, is this?
Because it's moving, so
It's like, happy moving day, here's Rice Krispies.
Because he didn't want it anymore.
Alright. Beautiful. Sick?
From the beginning of this week, sleeping into and
The weather's too nice. Sleepy weather. Okay, continue? Yes? Okay. Now, we have some equations, of course, because it's physics. The activity A is proportional to the number of atoms n. The activity and number of atoms are always decreasing in time. So mathematically, the activity is equal to minus a constant times the number of atoms. So wait, before you write that down, let me just draw a little picture here. Oh my goodness. So here the number of radioactive atoms is decreasing, and also the activity is decreasing. So both of these numbers are getting smaller, okay? And in fact they have a relationship. The bigger the n, the bigger the A. The smaller the n, the smaller the A. And the relationship is direct. A is equal to a constant multiplied by n. So if you double the n, then you double the A. If you half the n, then you half the A. There's a direct relationship between the activity and the number of radioactive atoms. Now the minus is what I was saying earlier. The minus just means that we're losing the atoms. Here, the A should equal a minus number. Yeah. But in the answer, you don't have to write the minus if you say destruction is or destroyed is. You know, it's like with acceleration and deceleration. Yeah. Okay, so this is our first formula for this lesson. A equals minus lambda n. Lambda is a positive constant known as the decay constant. And the minus is to show that n is decreasing. Yeah. Where'd you go? Okay, continue.
No. I remember the restaurant I told you before, it's not very
Of course.
It's coming soon.
Pitts Brothers?
Yeah, I can't remember the name, but
The meat restaurant.
no.
Meat.
No, fish and chips.
Oh, fish and chips restaurant, yes.
And I said it's closed.
It's coming back?
Yeah.
Oh, exciting.
But now looks like coming back. But the sign kept coming back.
Then it's coming back. Maybe they just closed it to redecorate.
Not so good.
Oh, yeah. You should take someone.
Where is it?
City Centre? Near O'Connell Street?
Yeah.
Is it Bishop Road?
Bishop, is it?
I can't remember. I can go to look at it.
Yeah.
Tomorrow.
So the important question is, who will you take?
Myself.
No. You should take someone. Let's see. Who would be good to take? You can't take him. He has a girlfriend. No good. No.
60.
No. You need to take, let me see. See, the business students, not many nice ones. Let me see. No, you should take a science student, because they're going to be a doctor. That would be useful. Okay, you have this? Yeah, me too. I don't want to be here. I want to be at home watching TV
Celebrate.
and celebrating.
Watch the show again.
Yes, watch it again. Yeah. Okay, you got this now, Amanda?
Yes.
Yeah. Right. Here's a question I want you to try. It's short, but I want you to tell me what the units for the lambda are. Okay, try to work it out, the units for lambda.
What is that?
Number of atoms. Are you finished, Sophie?
No.
Nobody knows?
DQ.
No. Maybe.
Okay,
Let's have a look.
1
So you have A equals minus lambda n. So lambda equals minus A over n. So the units for lambda, the activity, remember, is BQ, and the n is number of atoms. But what is a BQ? It's atoms destroyed per second. So you're left with per second, which is, yes, Grace, you're right, hertz, like frequency. So per second is the unit. Are you surprised you're right? So surprised? Per second, the hertz. Okay, continue? No? I saw that drink in the shop. Is it nice? No, the drink, the tea with honey, isn't it? Yeah. Is it nice?
Okay.
It's okay? Yeah. I saw it in the shop on the weekend. I'm like, maybe I should try it.
It's very famous, so.
Decorate.
It looks nice.
Because of the
Yeah.
design.
Yeah. But does it taste nice?
Yeah, but it tastes nice, so.
You tried them? Do you have a favorite flavor?
No, I've only tried one.
Which one?
I can't remember. But
I see the one I saw was something like Chinese tea and honey or something.
the one I drank was like green.
Yeah, the green one.
The green one with honey.
I don't know.
Yeah. This is good? Okay. Maybe I'll try it.
It's something like some kind of soft drink.
You only like Coke.
No, not all Coke.
No, only Coke?
Ice lemon tea.
Yeah.
Ice lemon tea?
Same
Okay.
thing.
Oh, okay. Maybe I'll try it. Since it's sunny. Okay. In a radioactive sample, 1 mole of atoms is destroyed into alpha, beta, and gamma radiation in 1 second. What's the activity of this sample at this moment? Okay. So if you can write this one down, and I'll do it. It's quite short, but I'll do it. Okay, can I do it now? Yeah? So I just want to be very clear about what's happening. So for example, you have your uranium. Hey, look. Do you remember in one of your homework questions, it was something like you have uranium and then it turns into lead plus so many alphas plus so many betas. Do you remember that? That was the last question. So what's happening is some of this uranium turns into lead. So it's not radioactive. It's the uranium is destroyed and it becomes lead. So then what happens is you get your alpha and your beta and your gamma then. Now in the question, how much uranium is destroyed? What did I say? I said 1 mole per second. Yeah. Now how big is a mole? That is Avogadro's number of atoms per second. How big is Avogadro? It's 6.02 times 23, isn't it? Per second. Atoms are destroyed. So this is the answer. The answer is 6.02 times 10 to the 23 equals atoms per second. This is the activity, and I'll put in the minus to show that it's being destroyed. How many atoms per second? Yeah, destroyed. Yeah.
How big? Do you measure with something?
Yeah, usually the numbers are megabequals or kilobequals. This type of number.
How can't measure how big is one?
How big?
Yeah.
What? Do you mean to look at?
If we measure
How big this way?
yes.
Oh, I even think, for example, 1 megabequal, I still think will be very, very small. Like, oh, you couldn't see it. It's so small because atoms are so small. So I think 1 megabequal, you can't even see it. It's so small. I think you would need, megabequal is 10 to the 6 mega. I think you would need at least something like 10 to the 24 or 25 before you could see it. But it's usually this, and this is too small to see. But you can measure it, and I don't even think you can't. You remember I said it's colorless.
Yeah, I
So if we could see it, we still couldn't see it because it's so small. Yeah.
One molar is in 1 mole there are 1 overall measurement.
Yeah. Oh, but you know this from Lorraine. She told you this, right? A long time ago. And Stephen told you this also, long time ago, back in semester 1. Yeah. You did Avogadro in semester 1, yeah? So long ago, huh?
I can't remember.
I know, yeah. Okay, continue? Right, so, try this one for me. Maybe you can do it. Hurrian, remind me, what's your university choice? I forgot. But what course?
Chemical engineering.
So, radiation might be something that comes up in this again. And what's your choice?
Bioengineering.
This will definitely be in bioengineering. So I don't think there's much radiation in aerospace. And Amanda, there's no radiation in computer science. In bioengineering and in chemical engineering, you'll probably study radiation again. Later we'll learn what's useful about radiation, how you can use it a useful way.
Microwave.
No, it's not. No, radiation would be like treating cancer, things, chemotherapy, stuff like this. Yeah. Yes, true. Yeah. So there are good things and bad things about it. Yes, that would be a bad thing. For example, did you know? You see here the smoke detectors. They have radiation in them. Well, just don't eat them. You'll be okay. Yeah. So there are good things about radiation, but it's usually bad. Yeah, we'll see that in a different lesson. Yeah. But what I mean is, some things in your home, like the smoke alarm, has radioactive material in it. Smoke alarm? Yeah.
Smoke alarm in my home.
Yeah.
Usually after taking shower, we open the door.
I have the same problem at home. So you have to leave the window open or
Close door.
alarm goes off. Yes.
And keep beep for all night.
Yes. Same problem. Cheap smoke alarm. Right. Do you have this one finished? No. Half finished. Okay. I don't think you need the calculator for this one.
No,
I think Avogadro's number is on the calculator though. But you don't need Avogadro's for this. No, you don't need Avogadro for this. Okay.
Which one?
Avogadro? It's NA, I think.
Oh,
Hmm.
for this one.
Finished?
Wait.
So Grace, what time are you free at today? 12 o'clock?
After
For 1 hour?
2 hours.
2 hours. You can come to D213, you know the big classroom? I have the business students at this time, but we're going to be working on the maths assignment, so I can, if you want, you could come into this class. In fact, actually, if any of you want to go to my next class, or maybe not you, because I know what you'll do in this class, you'll just sit beside your friend and not do any work. In the next class I have the business students, and I'm going to show them how to use Excel to do things. It might be useful for you for your physics lab report, because I'll be doing some examples of making graphs in Excel, so maybe you want to see it, I don't know.
Monday.
Fine. Okay, is this finished? Finished? Right, let's see. You have A equals minus lambda n. Lambda equals minus A over n, which equals minus 1000 over 10 power 10. For the n, wasn't it? So it's minus 10 3 over 10 10. So that's minus 10 minus 7. So the answer is lambda is 1 times 10 to the minus 7 per second. See? Easy peasy.
Shouldn't remember.
Too heavy? It'll make you strong. Okay, next. Huh? 1, and that's a formula, and then that's a question, and then it's a homework. Yeah, there's still a little bit more. Okay, this is one I want you to try. So, wait, let me read it first before you write it down. I want you to define activity by using this definition to express A in the form of a derivative. Hint, for example, remember, force is the rate of change of momentum. That is dp dt. Actually, you know what? No, don't bother doing that. I'll just give it to you. So, if you remember, activity is number of atoms destroyed per second. Yeah? So you can actually write it as a derivative. That would be dn dt, because this is how many atoms are lost, and this is per second. If you remember, it's a bit like when we said force is dp dt. Well, I think we said delta n, delta t, delta p, delta t. So this is another definition for activity. You can say activity is the rate of change of n, the n dt. This is another way to say it, okay? So please just note this result. Okay, you got that? Continue? Okay. Right. So to find the value of n or a at any time, we can use the radioactive decay equation. But the only problem is this equation doesn't have time in it. So, for example, let me go back here. A equals minus lambda n. Now, if you knew the n, then you know the a. Or, of course, if you knew the a, then you know the n. But what if you don't know a and n? What if you only know the t, the time? So we want to make a formula that has time in it. Okay? So, we can use the definition I just gave you for a. What does a equal? dn dt. Oh, so if you want to know, this is a bit like a proof. Yeah. Now, have you seen this type of problem in maths before?
Oh, yes.
What's it called? No, you've done it with Joan in semester 2. Ordinary differential equation. Do you remember this lesson, ODE, with Joan? So what do you do first here to solve this? Yeah, so what will I do first, Sohi? Okay. I will bring the n to the left and the dt to the right. So I bring this one up and I bring this one down and I make this. You did this with Joan.
Yeah.
You remember this?
I just remember the name.
Oh, fine. So you believe me when I say you did it with Joan, but you don't remember what to do. Great. So, next step, any ideas?
Move the n.
No? Integrate, thank you. So what do I get here when I...
1 over n.
What does this become? Yeah, integrate 1 over n dn, yeah, and this one here is integrate lambda. So, what do we get here? What does this become?
N by...
No.
Ln.
Thank you, log
Log n.
n. And what does this become?
1.
Lambda
Plus 2.
No,
lambda over...
no.
1 over no?
No,
It's just,
no,
it's just
no,
it's just,
no,
it's 1.
no. It's a constant. Yeah, like if I integrate 4, what do I get?
C.
4x.
Oh, F.
So lambda becomes lambda t plus
C.
c. Great. Now what do I do next if I want the n?
Just plus C over there.
No, it doesn't matter which side actually.
E. Oh, log.
Put e on both sides. So put an e here and an e here. So you get n equals e minus lambda t plus c. N equals EC, E minus lambda t. Now, how do we find the C? How do you find the C for these problems?
Put log again.
No, you have to use a point. So, for example, when t equals 0, we'll say that n equals n0. So we'll say at the beginning we have n0 atoms. Does that make sense? At the beginning, when t is 0, we'll say that n is n0. We'll have n0 atoms. Does that make sense? Yeah. Okay. So if I put this in here, I get n0 equals E0, e power 0. What's e power 0? 1. So what does EC equal? N0. EC is N0. So I can put that back in here. And I get N equals N0 E minus lambda T. This is the result. So now we have a formula for N if we know the T. Also, we can do the same thing for A. We can get a formula for activity if we know the T. No, the proof isn't on the exam, but it's good to know where it comes from.
Online book.
I think so. Okay? You've seen problems like this before in physics, these types of equations. Do you remember where? You do. Remember? I equals I0 E minus T over time constant. Do you remember this one? V equals V0 E minus time over time constant. Tau, yes? Not A, sorry. What else? Do we have anything else that's like this? Was there something else? Or no? Not Q, that was the other one, wasn't it? Q equals Q0 E minus T over time constant. So my point is, we've seen this type of equation before. It's not something new. In other words, in physics it's common to see something like this. Thing equals thing at the start, E minus a constant multiplied by time. Do you remember, like, this is a common thing in physics, that you have something and it equals what it was at the start multiplied by e power minus a constant multiplied by time. And you will see this again in physics. It's a common form of an equation in physics. Do you remember the other thing I said that was common in physics? The other one was thing equals constant multiplied by thing 1 multiplied by thing 2 over distance squared. This is another common form in physics. Yeah? You look confused. like I'm shocking you. For example, F equals GMN over R squared, or F equals K Q1 Q2 over R squared. Yeah? Yeah? Okay. Anyway, we have our decay equations. Here they are here. These are the two of them. Okay. You have those two written down? Make sure you have these two. I just proved them. There's the proof, yeah. Do you know what graph this makes? The graph? No.
But it's exponential.
Yeah. But it's exponential with a minus power. No. No, we'll look at that next time maybe. Continue. Right, so look, we have one question, and I think we might finish with... Yeah. Wait, so the best way to do this is if you just write down the information on part A, and we'll just do it bit by bit. So just write down until part A. Leave a space for the answer.
Can we write all the questions and then that?
No.
So we do all the answers.
You would rather do it that way?
So you have to go back to the question.
What? I don't know what you're saying. Just write down to part A, please. You're confusing me. Where's my calculator? I keep forgetting it. Disgraceful. Okay, do you have A part? No. Just A part, please. Do you have A part? Yes? Okay. Sophie, you have part A? Yeah. Okay, let's do it together. Do you know this material, iodine? I do. You did it with Lorraine? What's special about it?
It's blue. It turns blue.
Sorry, of all the things you could have said, being blue makes it special. Does it? What else? Go on. Does it do anything interesting?
It is a halogen.
Good, okay, now we're talking. So, in other words, you have done it with Lorraine.
Yes.
So, iodine 134 has a mass of, you have 268 grams of it. Now, the molar mass is 134 grams, and the decay at the start is 1.32 times 10 to the 20 equals. Okay, part A. I think we can all do this easily together. How many moles of iodine do you have? No, you don't need to write anything. You can see it in the information. No, don't even type anything. How many moles of iodine do you have? 2.
Yes.
2 moles. Because you have 268 grams and molar mass is 134 grams. So you have 2 moles of iodine. So part A is 2. So 2, please. Okay, now write down B. You got B? How many atoms do you have? How can you find this? How many moles do you have? 2. So how many atoms do you have? 2 Avogadros. So can you calculate that? Because I don't have a calculator. It's going to be something like, I know, you do it for me. I trust you. 2 multiply Avogadro, which is constant 20, what was it, 24? Okay, so let me write that one down. Let me put it down. So A was 2 moles, B was 1.2.
2044 multiply 10 power 24.
Okay. Part C. Write C down, please. What is the decay constant? For B? Do you know how we got it? Yeah. Okay. C. What is the decay constant? Okay, can I do C? Yeah. So C, what is the decay constant? And what formula can we use? A equals minus lambda n. So lambda equals A minus A over n. Now A, listen. Remember in my definition I said all lambda is always positive, okay? So you want this to be positive. So if I have a minus here, the activity, we must make it minus. So in total we have positive. What did I say the activity was at the, let me write down here. What was the activity at the start? I gave it in the question. What was it? 1.32 times 10 to the 20. And the n is 1.204 times 10 to the 24. So what do we get in total, please? It's going to be 1.1 or something. Yeah, so 1.1 times 10 to the minus 6? Minus 4, sorry. Per second. Okay. Can I go back to the question? D, write that down. How many atoms do you have after 1 hour? Okay, so what formula can I use for D? How many atoms after 1 hour? That's it. N0 E minus lambda T. So what's our N0? How many atoms do we have at the start? That's 1.204 times 10 to the 24 times E power minus lambda. And what's the T? 3,600. Yeah?
I put wrong. I guess so.
Why? What?
It's
Give me, let me see what you think. What? Yes, 10 power minus 4. Oh! Bad teacher. Minus 4. There we go. 6.89 times 1023. I don't know.
I'm supposed to put
What?
the first number in bracket.
Shouldn't matter for this, because they're multiplied.
Okay.
I get this one.
Huh.
What's the number and then?
800.
Yeah, I got that too.
Oh.
You just have to.
1.2. 204. You were 8.1. Thank you. Okay, continue. Now, part F. How long until only 100 grams of iodine are left?
What about E?
E? Oh, what's the activity after 1 hour? Well, we can just use our formula A equals minus lambda n, that equals minus 1.1 times 10 to the minus 4, multiplied by 8.1 times 10 to the 23. So what's that? That's, I don't know, that's going to be 8.9. Huh? Oh, sorry, you didn't have a chance to write down, sorry. What is the activity after 1 hour? I don't know. I don't have a calculator. Can you type it in? It's going to be minus 8.91
Yes.
times 10 to the 19
Yes.
equals. Smart. Okay. F. How long until only 100 grams are left? Okay. Can I do this one? So, you know that n equals n0 e minus lambda t. And what's n here? What's n? Number of atoms. Sorry, that's what does n represent? And what's A? Activity. A0 e minus lambda t. So you won't be surprised to know that you can do this also for mass. You can say the mass equals the mass at the start, E minus lambda t. And the proof, you can easily show it from this formula here. And maybe I gave that as a homework question actually. Anyways, how much mass do we want? 100 grams. And how much do we start with? 268. And what's the lambda? 1.1 times 10 to the minus 4 t. Now, have you seen this type of problem in maths and in physics before? Yes. How do we get the t? What do we need to use? We need to use log, don't we? So we have 0.100 divided by 0.268. That's equal to e minus 1.1 times 10 to the minus 4t. So we put a log here, cancel, cancel, we put a log here. So then we just divide by this, and now we have our t. So I don't know what that is. Maybe you can type that in, Hareen. I don't know. Should get something like, I don't know, like 6,000 or something. What did you get? Yeah, it should be a big number. What did you get?
8,961.
Seconds. Yeah. Yeah.
Oh, yes.
Yeah. Okay, can I do the last part, please? Yeah. So the last part. How long until the sample is 1/4 as active than it was at the beginning?
Initially.
Yes. Yeah? Okay, can I do this one? Right, so what formula do I need for the last part, G? A equals A0 E minus lambda T. Now, what's this A?
1.1 times.
No, that's the A after 1 hour, is it?
Alright.
1.1.
That's the A at the beginning, is it?
Yes.
Now look, listen. I don't need to know what the A is because I want to know when is this A 1/4 of the value at the beginning. So I can do it like this. And you see now I don't need to know the A because I can just cancel. Do you understand what I do? So what's next? What do I do next? Log 1/4 equals minus lambda t. So t equals log 1/4 divided by minus 1.1 times 10 to the minus 4. How many seconds is that now? No calculator, Sophie? Ah, forget it. 1, 2, 12,000 seconds. Can you divide by 3,600? How many hours is that actually? 3 hours. So after 3 hours, the activity is only 1/4 what it was at the beginning. Yeah? Okay. Continue? Homework. Grace, wait, maybe you can, oh no, wait, I'll move the projector a little bit because it's hard for me to put off.
Sorry,
Fine.
don't want to go to business class.
No, why would you? Those business students. Oh. Go get some coffee. Can I close this? Yes? Okay.